Hello, in this video we are going to work on rate of change. So, rate of change is the measure of how one variable changes with respect to another. So, speed is a rate of change that measures how distance changes with respect to time. In general, we talk about the rate of change of y with respect to x. So, a linear function has a constant rate of change. It's the slope of the function. So, for this linear function, we can see the next clear point is here. So, we have risen 3 with a run of 1, so the slope is 3 over 1, or 3. And this is constant. For every point along this, for every x value along this function, the y value is changing at a rate of 3 over 1. But for a nonlinear function, the rate of change varies depending on the value of x. So then for a nonlinear function, f at x, the rate of change is itself a function of x. So here we can see the differences. So we have a function that at first is decreasing, and then after the turning point it is increasing. So when the rate of change is positive, our function is increasing. And when it's negative, our function is decreasing. And when the rate of change equals to 0, the function has a turning point. So we can find two types of rate of change. So the average rate of change is between 2 points on a curve, and it's the slope of a line between those 2 points. This line is called the secant line. So really all it is for this function, you'll draw a line between those 2 points. And the rate of change is the slope of that line, which is the difference in the y values divided by the difference in the x values. You could also write it as y2 minus y1 over x2 minus x1. It's just our slope formula. So the rate of change of x over the interval from 0 to 9 will be, so the y value when x is 9 is 3. And the y value when x is 0 is minus 7. So we're going to do 3 minus 7, 9 minus 0. So that's 10 over 9. So this function from this interval of 0 to 9 has a rate of change of 10 over 9. Note that this is really very general because it's showing overall the function has increased, like the rate of change is positive, but we can see many dips and changes in the rate of change. What we drew here is the secant line, so a line that joins 2 points. Yeah, we can also find the average rate of change by just using equations. So what is the slope of the secant? So that's also average rate of change. Okay, so the slope of the secant, actually, since we're doing slope, I'm going to call it m. Okay, and we want to go between -1 and 3, so it'll be f at 3 minus f at -1, and the difference in our x's will be 3 minus -1. So f at 3, putting this into a calculator, you get minus 52, and f at -1 gives you minus 4. So we're going to do minus 52 minus 4 divided by 4. So minus 52 plus 4 is minus 48 over 4. And simplifying this means we have a slope of minus 12. So the second type of rate of change is the instantaneous rate of change, and it's the rate of change at a point, and it's the slope of the tangent. So we have to approximate this value using the average rate of change formula with 2 points very close to each other. So right now we're starting with the point x, and then h is some distance away from x. Right now, the second point is pretty far away, so there's a pretty big distance between the 2 points, and you can see what we've drawn is a secant. But if we make this h smaller and smaller and smaller and smaller, then when I draw the secant, it actually begins to look like, that's not very good. But what I've drawn is a tangent line, and a tangent line is a line that touches the curve at 1 point. So we still use the slope formula, but our second point is going to be really close to our first point, and we will give this distance 0.001 away. So if x is 3, we're going to use the point next to it of 3.001. Okay, so let's approximate the instantaneous rate of change of this parabola. So again, it's delta f at x over delta x, and it's approximately f at 2.001 minus f at 2, and it's going to be over our h, which is 0.001. So using your calculator, 2.001 squared plus 3 is 7.004001. And then just 2 squared plus 3 is 7, all over 0.001. And plug that in, it's 4.001, which is giving us a rate of change of about 4. So that is our instantaneous rate of change is at a point, and the point's really close to the given point. And then average rate of change is between 2 points. So let's do a little summary. So we've got the height of a toy rocket is given this equation. Time is in seconds since takeoff of the rocket. I guess toy rockets have takeoff. Anyways, the time when a kid presses the launch button. And h is the height in meters. So the average rate of change from 0 to 4 seconds will be the change in height over the change in time. So it'll be h at 4 minus h at 0 over 4 minus 0. So h at 4 in your calculator is 241.6 minus 0 over 4. And this gives us a value of about 60.4, and our units are in meters per second. So actually at 2 seconds, what's happening? So let's approximate that instantaneous rate of change. And it's going to be h at 2.001 minus h at 2 divided by 0.001. And with our calculator, it actually gives us the same value as the average rate of change from 0 to 4. So what does the rate of change mean in each part? So the average rate of change, it's the average speed, and that's 60.4 meters per second for the first 4 seconds. Okay, and IROC means that at exactly 2 seconds, the speed is 60.4 meters per second. So what are the limitations in approximating the average and instantaneous rate of change as a function? So the average is really not very descriptive. So if we're going to use rate of change to tell us about like how a function is changing, and remember this example, if we just say that the rate of change is 10 over 9 between 0 and 9, it's really not descriptive of all the different increasing and decreasing intervals and turning points that are happening. When we do the instantaneous rate of change, sorry for all the scrolling, we can kind of get stuck, like how close is close enough? Here we've chosen the points to be within 0.001 of each other, but should we choose even closer, like 0.0001? And what happens as we go closer and closer? What happens is that we still are approximating the rate of change. Okay, and the approximations can be very good as you get closer and closer, but is an approximation ever good enough? So to get a more accurate calculation with the IROC, we can get smaller and smaller, h values, basically until h is 0. We really want h to basically be 0. Okay, and when we figure out how to put h at basically 0, this is calculus. This is one of the main ideas of calculus. This is calculating the derivative. Okay, so on that note, I will end the course of advanced functions with a hint of things to come for those of you who are taking calculus.